Hi guys, I've put another video together on conjugate pairs because it is a concept that comes up quite often, and I sort of touched on it in the previous video, but this time I want to just look at it in a little bit more detail. It's going to be important for understanding acid-base equilibria and also for understanding the function of buffers. We've seen too that when you're looking at indicators, indicators too can be understood in terms of conjugate acid-base pairs. So let's have a look at these in a bit more detail now. So firstly, a definition: conjugate pairs are a species involved in the transfer of protons. So in general, what we're looking at is an acid transferring, change the color over here for a minute and make that a little bit better. So generally speaking, you have acid 1 going with conjugate base 1 and base 2 going with conjugate acid 2. And the reason for that is the H+. So we can tell what's going on with our conjugate pairs in terms of what's happening to the H+ ions. So here, an acid is a species that donates, so it loses the H+ ion, which it's going to give to the base, and this will be what happens after it's lost the H+, and the conjugate acid will be what's happened after a species has gained an H+. The equilibrium position of an acid-base system is determined by the relative strengths of the bases involved, and that, of course, can also apply to the acids involved. So it's very much dependent on what's going on, which species is good at donating and which species is good at accepting the protons. So a couple of things firstly in terms of definitions. Firstly, if we have an equilibrium which lies to the right, then that means that the HA going to H+ and A- is going to be favoring the products, and you might remember when we did our Ka calculation, we put the concentration of the products on top of the reactants, and therefore if the equilibrium lies to the right, this is the larger of the two numbers, and therefore we will have lots of ions and not too many of the individual acid molecules. So one of the things that's important to understand then is that if we have a strong acid or a strong base, then we will have a weak conjugate. And of course, the reverse is true of each of these. So strong bases will have weak conjugate acids, and strong acids will have weak conjugate bases. So what applies to one group applies to the opposite. When the equilibrium lies to the left, that means that when we look at the products over the reactants, this time the reactants is large. And so therefore the equilibrium lies to the left, and the concentration of the H+ ions is, the HA molecules is much higher in relation to the A-. Okay, so we have an acid here, and A- would be its conjugate base. And so when the equilibrium lies to the left, we have much more of the molecular species than we do of the ions. And so, as we said above, strong bases have weak conjugate acids, and therefore strong acids also have weak conjugate bases. Likewise, if we look at weak substances, the weak acid has a strong conjugate base, and likewise a weak base has a strong conjugate acid. Now this probably doesn't mean very much to you at this point in time, but we are going to have a look at the salts created by these conjugate acids and bases, and the fact that they can actually affect the pH themselves. So let's look at acids and their conjugates. So the strength of an acid is a measure of its degree of ionization. So the stronger an acid is, the more readily it will ionize. The weaker an acid, the more you will find its molecular species dominating over its ion. So HCl therefore will be a strong acid, and the one underneath that is acetic acid or ethanoic acid, and that is a weak acid. So what we expect then is that the H plus that's being given off from the hydrochloric acid, I'll leave the subscripts out for the moment. This one's pretty much going to go to completion. So we have an H3O plus and a Cl minus. This underneath CH3COOH plus H2O. This one's an equilibrium, and we still have the H3O plus. But this time I'll just pop down here CH3COO minus. So here is the acid here, and here is the acid here, and this is the conjugate base, which left once the proton has disappeared, and this too is the conjugate base. So the important thing is when we're looking at acids, acids have the form HA, a hydrogen ion plus an anion joined together to form a molecular compound. So when they ionize, they liberate hydrogen ions, which is always going to be the case, and what we will be left with is a conjugate base. Okay, in this case it's a chloride ion, and in this case it's an acetate or ethanoate ion. We can do the same thing with bases. The strength of a base is a measure of its degree of ionization. So the term strength always refers to the same thing. It's just we talk about different chemical substances. So sodium hydroxide would be regarded as a strong base, and ammonia is a weak base. When we look at what happens, effectively this may sound a little bit silly, but the OH minus ions in water are going to produce water and OH minus. Sounds rather silly, but that is actually going to be a base which is going to accept a proton from there. And effectively we know that in water the molecular species dominates anyway, so nothing seems very much to be happening here other than we get a significant increase in the OH minus ions. A little bit tricky therefore to see with what's happening with sodium hydroxide in terms of acting as a base. Unless you actually put it with something like hydrochloric acid, then you can see what's happening much more significantly. But if we were to put ammonia in water, then what we would see very clearly how the ammonia acts as a base to accept a proton and leave us with the OH minus ion. So in this case we have a base and we have a conjugate acid. Okay, now effectively the OH minus ion has water as its conjugate acid. That kind of tells you something about the strength of the conjugate in this case. In this one, however, the weaker base of the ammonia produces a much stronger conjugate acid, the NH4+ ion. And of course, when this is forming salts, this can actually affect the pH of the solution when an ammonium salt is dissolved in water. So again, the key thing is we're looking at a base, we're looking at the anion this time, is accepting the proton. Okay, our Bronsted-Lowry definition is that bases are proton acceptors. So the bases are going to be accepting a proton and therefore producing a conjugate acid. So here's a question for you from the 2014 HSC. The following equation represents a chemical system in equilibrium. You may remember this particular system exists in swimming pools. Which of the following is an acid-base conjugate pair? Stop the tape and stop this video and see if you can have a go. Well, I hope you've had a go before you watch the rest of it, but even if you haven't, let's see if we can figure this out. So H2O is on the reactant side and HOCl is on the product side. So that's okay in terms of a pair, but there should be a relationship between an H+. When we're looking at conjugate pairs, the relationship is the H+. That's the thing that's most important, and there's certainly more than a hydrogen difference between these two, so that's no good. In the second one, both of these two species are on the product side, and therefore they can't be conjugates because they're both on the same side. A conjugate has to be the result of either the gaining or losing of a proton, and as a consequence of that, there has to be something on either side of our equation. So that can't be the case. The third one is a possibility. In this case, we have an HOCl molecule and an OCl- ion. The difference between these two is an H+. So the H+ is lost from the HOCl. That means we lose a hydrogen and we go down a charge. So if this is our little number plane, we go 1 and -1. So if we go down one charge, down this becomes a negative. And that's exactly what we have here, which means this must be correct. And again, the last one, both of these are on either side. We have a reactant and we've got two reactants. So they're both on the same side of both reactants, and therefore it too can't be right. So the correct response here is response C. Thank you for watching.